This lesson is going to explain theorems about roots of polynomial equations, including the rational root theorem, conjugate root theorem, and Descartes' rule of signs. Okay, so first we're going to talk about the rational root theorem. The standard form of a polynomial equation is ax cubed plus bx squared plus cx plus d. And d will always be the constant. A will be the leading coefficient. And to find all the possible rational roots, for the rational root theorem, you will use the constant and the leading coefficient. And the form will be the factor of the constant divided by the factor of the leading coefficient. This problem is going to be our example, and the 2 is the constant in this polynomial equation. And then 15 is the leading coefficient. The factors of 2 would be 1 and 2, while the factors of 15 will be 1, 3, 5, and 15. So now we're going to use the form factors of a constant over the factors of the leading coefficient. So you're kind of just going to distribute the factors of the constant over to the factors of the leading coefficient. Then you get all of these numbers, which is all of the possible rational roots. And the way you know something is a possible rational root is if it equals 0 when you insert it back into the equation. Here 1 is plugged in, but it equals -12, so it's not a root. But when you plug in 2, it does equal 0, so you know that that is one of the roots. So after you find one of the roots, if it's not a fraction, you could do synthetic division to kind of factor out that. If you do get a fraction, like let's say you got 1/3 as a root, you would have to do polynomial long division. But if you get a whole number, you can do synthetic division. So once you do divide it, it's going to turn out to be x minus 2. Then you're going to get 15x squared minus 2x minus 1. And if you don't get a 0 at the end, then there's a good chance you might have made a mistake. So always make sure that there's a 0 at the end. So 15x squared minus 2x minus 1. And you're going to just factor that out as you normally would, and then set each factor to 0 and solve, and that will be your remaining rational roots. So the rational roots would be 2, that we can't forget, -1/5, and 1/3.
Here's a song to help you remember the rational root theorem. When you try to solve a polynomial equation, but all you end up is sad and frustration, there's a trick that can help you, so let's hear 'em. It's called the rational root theorem. First step to find the roots is to find the factors of the constant term and leading coefficient. Then you just perform some simple division. Put the constant over the coefficient and come up with possible roots. We're not done yet, we have to simplify or it'll all be for no use. Once you simplify, you have solved for the answer. Remember, the more you practice, you can solve possible roots easier and faster.
This is Descartes' rule of signs. And Descartes' rule of signs basically tells you how many positive roots you will have and how many negative roots you will have depending on the sign changes. Well, basically what all of this means is the number of positive roots is equal to the amount of sign changes when x is positive minus 2 repeatedly. And the number of negative roots is equal to the amount of sign changes when x is negative minus 2 repeatedly. So this is just a regular polynomial. You could do the rational root theorem, but we're going to do this Descartes' rule of signs first so we could find out how many positive and negative roots there will be. So I like to write a little plus sign at the beginning if x is, a plus, because it just helps me remember. And so now you're going to count the sign changes. So plus to a minus, that is one sign change. Minus to a plus is the second sign change. So since x is positive, there will be 2 positive roots because there are 2 sign changes. But you also minus 2 repeatedly. So also, since x is positive, there will be 0 positive roots. That's a possibility too. So since x is positive, there will be 2 or 0 positive roots. There's no way of knowing whether you're going to get 2 positive or 0 positive, but it's just an idea. So now we're going to find negative roots. So when you find the negative roots, you first have to plug in negative x into wherever x shows up. It's going to be negative x. And it's a good idea to insert this with parentheses because it could get a little confusing sometimes. So negative x cubed we know is going to be negative x. Negative x squared will be positive x, but since there's a negative sign, it will still be negative x squared. And then plus 1 equals 0. So now we're going to count the sign changes. So negative to negative, no sign change. Negative to positive, 1 sign change. So since x is negative, there will be 1 negative root. Minus 2 repeatedly, if you do have 1, there's no way of trying to subtract 2, so you just leave it at 1. So now you know for this equation there's 2 or 0 positive roots and 1 negative root.
Here's a song to help you remember Descartes' rule of signs. Next thing I'm going to teach you is Descartes' rule of signs. First, clean up the equation, put it in standard form. Great, you're almost there. Here's the next thing you'll perform. Take a look at what you're left with and look at the sign changes. Now you've got your positive. Let's find the negative. To find the negative, we have to edit it. We substitute negative x in place of x and simplify the equation, then count the sign changes and you found your negative. You completed Descartes' sign of rules. What a great occasion.
Alright, so now we're going to put Descartes' rule of signs and the rational root theorem together. So first, the rational root theorem. This 5 is our constant, 6 is our leading coefficient, and you have the factors 1 and 5 of the constant, and then the factors of the leading coefficient. So now you could just distribute all of the constants over to the leading coefficients. If you do Descartes' rule of sign, you could find that there's 1 positive root and 2 or 0 negative roots. So next, this is the same problem. So now we're going to try to find a root that suits the equation. So just keep inserting. Here I found negative 5 suits the makes the equation equal 0, so that's 1 root that you have there already. And also you have to write it in this form right here, x plus 5, even though the number is x minus 5, because it's x minus 5. So synthetic division, I just divided negative 5 and found 6x squared plus x minus 1. And if you factored this even further, you'll find x plus 5, 2x plus 1, and 3x minus 1. And if you set both of these to 0, you will find that they equal negative 1/2 and 1/3. And don't forget the negative 5. And these are all your roots. So the last theorem is the conjugate root theorem. This is the actual conjugate root theorem, but I like to write in my own words to try to make sense of it. So if a complex number or an irrational number, which is usually a radical, is a root of a polynomial equation with rational coefficients, so is its conjugate. If it's radical 3, then the conjugate will be negative radical 3. If it's 3 plus radical 4, then the conjugate will be minus 2 plus I, 2 minus I, 3I will be negative 3I. So those are just how the conjugates work for irrational numbers.
Let's take a look at this example. Suppose a polynomial equation with a degree of 11 have roots of 2i and 1 plus I. So if it has a degree of 11, it'll have to have 11 roots. According to the conjugate theorem, the roots occur in pairs. The conjugate of 2i would be negative 2i, and the conjugate of 1 plus I is 1 minus I. So we know that some other roots are negative 2i and 1 minus I. We already know that it has 2 non-real roots and the conjugate pairs of them, so we know that it has 4 non-real roots. It has 11 roots, so the number of real roots it can have is 11 minus 4, which is 7. So it can have 7 real roots at maximum. There are 11 roots, and we know it has 4 non-real roots already. The rest can be non-real as well, but remember that they have to occur in pairs, so that it'll have to be an even number. 11 is odd, so 10 would have to be the maximum number of non-real roots it can have.